Hello, friend. Welcome to Science for Sleep. Did you know that technically we are still in an ice age? Tonight, we're going to spend some quiet time with a very slow story. One that unfolds over distances too wide to measure with footsteps, and over time too long to feel with a single lifetime. We're exploring ice ages. The kind of cold that doesn't arrive like weather, but like a gradual drift. A change so patient that the world has time to adjust around it. To picture an ice age, it helps to imagine the planet gently changing its balance between snow that stays and snow that melts. When summers are cool enough in certain regions, winter snow can linger. If that happens year after year, the lingering snow compresses into denser layers. Over long stretches of time, those layers can become ice. And once enough ice builds, it begins to move under its own weight, slowly spreading outward like a thick, quiet river. One of the most surprising facts is that an ice age is not the same thing as a single frozen era where everything stays locked in ice. In science, an ice age is a long period when Earth has large, permanent ice sheets somewhere on the planet. Inside an ice age, the climate shifts back and forth between colder phases, called glacial periods, and warmer phases, called interglacial periods. That means an ice age can contain both the deep cold of expanding ice and the gentler warmth of retreating ice. And in that sense, Earth is still in an ice age right now. We live in a warmer interglacial phase called the Holocene, which began a little over 11,000 years ago, after the last major glacial period eased back. Even today, the planet still holds long-lasting ice in places like Antarctica and Greenland. Those bright, quiet sheets are part of what makes this current era an ice age in the scientific sense. As you settle into this topic, you can imagine the world as a set of layers. Air above, ocean below, land in between, and then, in the coldest places, a slow accumulation of snow that becomes a record. Each year's snowfall can press into the next, forming a soft archive. Over time, the archive becomes firm, then icy, then deep and compact. And inside that ice, tiny bubbles of ancient air can be trapped and preserved, holding clues about the atmosphere long ago. This is one way scientists can study past climates with remarkable detail, because the ice keeps the evidence sheltered and still. Ice ages are also tracked in the shapes left behind on the land. When glaciers move, they scrape and polish rock. They can carve wide valleys with smooth curves, and they can push piles of rubble into ridges called moraines. Even when the ice is gone, the landscape keeps the memory of its motion, like faint lines on stone that remain long after the tool has passed. If you enjoy these quiet journeys, you're welcome to subscribe. And if it feels natural, to leave a comment sharing where you're listening from tonight. It helps others find their way to this calm corner of the world, one sleepy traveler at a time. The quiet continues here, just as it is. As we move gently forward, we'll keep returning to simple images like these. Snow staying a little longer than it used to. Layers slowly pressing together. Ice beginning to flow. Shorelines shifting as water is stored on land as ice, then released back into the ocean over long ages. The details will come slowly, in a way that gives your mind something steady to hold, without asking it to stay alert. And if your attention drifts, that's completely natural. This topic is built for drifting. Ice ages are patient by nature. They don't demand quick focus. They simply invite a softer kind of curiosity, the kind that can sit beside sleep without disturbing it. So for now, you can imagine the Earth from far away, quiet and round, with pale caps at the top and bottom. You can imagine seasons passing like slow breaths. And you can let the idea settle in that ice ages are chapters that unfold over deep time, shaped by balances and by gentle shifts that take thousands of years to become clear. As we continue, we widen the lens and let time stretch far beyond anything familiar. To understand ice ages fully, it helps to know that Earth has not experienced just one long cold chapter, but several, spaced across billions of years. Each one unfolded slowly, shaped by different arrangements of continents, oceans, air, and sunlight. When scientists speak about ice ages, they are often speaking in the language of deep time, where millions of years pass like pages turning. The earliest known ice age occurred more than 2 billion years ago, during a period called the Huronian. At that time, Earth was a very different place. The atmosphere contained far less oxygen than it does today, and life existed mostly as microscopic organisms in the oceans. Evidence from ancient rocks suggests that glaciers advanced and retreated repeatedly over hundreds of millions of years. These early ice ages may have been linked to changes in atmospheric gases as photosynthetic life slowly altered the chemistry of the air. Even here, the pattern is familiar. Cooling did not arrive all at once. It built gradually, stabilized, and eventually eased. Much later came one of the most extreme cold periods Earth has ever known, during the Cryogenian period, between about 720 and 635 million years ago. This is the time often associated with the idea of a nearly frozen planet. Geological clues suggest that ice may have reached very close to the equator. Glacial deposits found in what were once tropical regions point to a world where ice spread far beyond the poles. Yet even in this profound cold, Earth did not fall silent. Oceans likely remained liquid beneath the ice, and life persisted in sheltered environments. Eventually, volcanic activity released enough carbon dioxide into the atmosphere to help the planet warm again, allowing ice to retreat. After the Cryogenian, Earth entered long stretches of warmth. For hundreds of millions of years, ice was scarce or absent, and the planet supported lush forests, shallow seas, and diverse life forms. Then, around 300 million years ago, another major ice age arrived during the late Paleozoic era. This one coincided with the time when the continents were joined together in a vast landmass. Large glaciers formed across parts of what are now South America, Africa, Australia, and Antarctica. As before, the ice expanded and contracted in cycles, guided by slow changes in Earth's systems. When that ice age faded, warmth returned again. Dinosaurs would later walk across a largely ice-free world. Polar regions were forested and sea levels were high. This warm balance held for tens of millions of years until gradual tectonic changes set the stage for a new cold era. About 34 million years ago, Antarctica drifted into its current position over the South Pole. A powerful ocean current formed around it, isolating the continent and allowing a permanent ice sheet to grow. This moment marked an important step toward the ice age we live in today. The most recent ice age began roughly 3 million years ago, during the late part of the Cenozoic era. This is known as the Quaternary Ice Age. Unlike earlier ones, It is characterized by repeated advances and retreats of ice, especially across the northern hemisphere. Massive ice sheets spread over North America and northern Europe during colder glacial periods, then withdrew during warmer interglacial phases. These cycles repeated many times, each taking tens of thousands of years. The last major glacial period reached its peak around 20,000 years ago. At that time, ice covered much of Canada, the northern United States, and large parts of Europe. Sea levels were far lower than they are now, because so much water was locked into ice. Then, slowly and unevenly, the climate warmed. Ice retreated, coastlines shifted, and the world entered the current interglacial phase. Looking across this long timeline, a gentle pattern emerges. Ice ages are not anomalies or disasters. They are recurring states that arise when conditions allow ice to remain and grow. Each one has its own character, shaped by where continents sit, how oceans circulate, and how sunlight is distributed across the planet. Some ice ages were global and extreme. Others were more regional and moderate, but all followed the same patient logic. As you rest with this idea, you might imagine Earth as a traveler moving through different climates, never staying fixed for long in geological terms. Cold comes, warmth returns, and life adjusts each time. The planet does not rush these transitions. It allows them to unfold at a pace that feels almost still. And with that perspective, ice ages become less like distant catastrophes and more like long seasons in Earth's deep calendar. Seasons that last not months, but millions of years. Seasons that leave their traces quietly, in stone, in ice, and in the slow memory of the land. To understand why ice ages begin, it helps to let go of the idea of a single cause or a sudden trigger. Ice ages do not start because one thing changes all at once. Instead, they emerge when several slow processes line up in a way that allows cooling to build and persist. The planet doesn't flip a switch into cold. It gradually drifts there, guided by patterns that repeat over tens of thousands of years. One of the most important influences comes from Earth's motion through space. Although our planet's distance from the Sun stays within a narrow range, the shape of Earth's orbit, the tilt of its axis, and the direction that tilt points all change slowly over time. These movements are known as orbital cycles, and they affect how sunlight is distributed across the planet, rather than how much sunlight Earth receives overall. The first of these cycles involves the shape of Earth's orbit. Over about 100,000 years, Earth's path around the Sun shifts from being nearly circular to slightly more oval and back again. When the orbit is more stretched out, the difference between Earth's closest and farthest points from the Sun becomes greater. This doesn't dramatically change global temperatures, but it does subtly influence how energy is spread across seasons. Another cycle involves the tilt of Earth's axis. Right now, Earth is tilted at about 23.5 degrees. Over roughly 41,000 years, that tilt gently increases and decreases. When the tilt is smaller, summers in high-latitude regions become cooler. This matters because ice ages are especially sensitive to summer temperatures. If summers are cool enough that winter snow does not fully melt, snow can begin to accumulate year after year. That lingering snow is the first step toward growing ice sheets. The third cycle involves a slow wobble in the direction Earth's axis points, known as precession. Over about 23,000 years, this wobble changes the timing of seasons relative to Earth's position in its orbit. In some configurations, summers in the northern hemisphere occur when Earth is farther from the Sun, making them slightly cooler. In others, summers occur when Earth is closer, making them slightly warmer. Again, the difference is subtle, but over long periods, it can tip the balance between melting and accumulation. These orbital cycles work together, overlapping and reinforcing one another. When their combined effects lead to cooler summers in regions where ice can form, the conditions become favorable for glacial growth. Importantly, it is the coolness of summer, not the severity of winter, that matters most. Cold winters alone do not create ice ages. What matters is whether snow survives the summer. Once snow begins to persist, feedback processes take over. Snow and ice are very reflective. They bounce much of the sun's energy back into space. As reflective surfaces expand, less energy is absorbed by the land and oceans, leading to further cooling. This cooling allows even more snow to survive, reinforcing the cycle. This is known as the ice albedo feedback, and it plays a central role in turning small orbital changes into large climate shifts. Greenhouse gases also play an important supporting role. During the early stages of cooling, changes in ocean circulation and plant growth can gradually reduce the amount of carbon dioxide in the atmosphere. Ice core records show that carbon dioxide levels tend to fall during glacial periods and rise during warmer interglacials. These changes usually follow the initial temperature shifts rather than causing them, but they amplify the effects. Lower carbon dioxide allows more heat to escape into space, deepening the cold and helping ice sheets expand. The arrangement of continents adds another layer to the story. Ice ages are more likely when large landmasses sit near the poles, because land can accumulate ice more easily than ocean. Plate tectonics slowly rearrange the continents over millions of years, opening and closing ocean gateways and reshaping currents. These changes influence how heat moves around the planet. For example, when warm ocean currents are blocked or redirected, high-latitude regions can cool enough to support growing ice. Mountain building also contributes in quiet ways. As mountain ranges rise, they expose fresh rock to weathering. Rainwater reacting with this rock can remove carbon dioxide from the atmosphere over long periods, gradually cooling the climate. This process is slow and steady, operating over millions of years, but it helps set the background conditions that allow ice ages to emerge. When all these factors align, orbital shifts nudge temperatures downward, reflective ice spreads, greenhouse gases decline, and circulation patterns adjust. None of this happens quickly. The onset of an ice age can take thousands of years. To the planet, it is a gentle transition, a long easing into a colder rhythm. As you sit with this idea, you can imagine Earth responding not with drama, but with patience. Small changes accumulate. Feedbacks reinforce one another, and eventually, ice begins to shape the surface, quietly and persistently, as part of a cycle that has repeated many times before. When people think about ice ages, it's easy to imagine ice appearing suddenly, as if the world simply froze. But the way ice sheets actually form is far slower and far more delicate. Ice does not arrive all at once. It begins with something very ordinary: snow that stays. In regions where temperatures remain low enough year after year, snow can accumulate faster than it melts. This balance between snowfall and melting is the first requirement for building long-lasting ice. Even in cold places, snow can disappear each summer if temperatures rise just enough. For ice to form, summers must be cool enough that some of the previous winter's snow survives. That surviving snow becomes the foundation for everything that follows. As fresh snow falls on top of older layers, the weight of the overlying snow gently presses down. Over time, this pressure squeezes air out of the spaces between snowflakes. The snow crystals change shape, becoming more rounded and compact. This intermediate stage is called firn. Firn is not quite snow anymore, but it is not yet solid ice. It is denser, slightly granular, and still contains small pockets of air. This transformation from snow to firn can take decades, sometimes longer, depending on how much snow falls and how cold the region remains. As accumulation continues, firn slowly turns into glacial ice. The remaining air pockets are sealed off into tiny bubbles, preserving samples of the atmosphere from the time they formed. These bubbles are one of the reasons ice sheets are so valuable to science. They quietly store a history of Earth's climate, layer by layer, year by year, without disturbance. Once ice reaches a certain thickness, it begins to behave in an unexpected way. Despite its solid appearance, ice can flow. Under its own immense weight, glacial ice deforms and moves outward from its thickest points. This movement is extremely slow. In many places, ice creeps forward only a few centimeters or meters per day. But over centuries and millennia, this motion allows ice sheets to spread across vast areas of land. It's helpful to distinguish between different kinds of ice formations. Ice sheets are the largest. They cover areas the size of continents and can be several kilometers thick at their centers. Antarctica and Greenland are the two remaining ice sheets today. Ice caps are smaller versions, covering mountainous regions or plateaus. Glaciers are smaller still, flowing down valleys or spreading gently across plains. During ice ages, glaciers and ice sheets often connect, forming massive networks of ice that reshape the land beneath them. As ice flows, it interacts with the ground in subtle but powerful ways. Rocks frozen into the base of the ice act like sandpaper, slowly grinding against the surface below. This process smooths bedrock and carves wide valleys. Ice can also pluck blocks of stone from the ground, carrying them long distances before dropping them elsewhere. All of this happens without noise or sudden motion. The work of ice is steady, patient, and almost imperceptible in the moment. Temperature within an ice sheet varies with depth. Near the surface, ice remains extremely cold and brittle. Deeper down, pressure and geothermal heat from the Earth can warm the ice slightly, making it more flexible. In some places, thin layers of meltwater form at the base of the ice, allowing it to slide more easily over the ground. These conditions affect how quickly ice moves and how it shapes the landscape. The growth of an ice sheet is not uniform. Some areas accumulate snow more quickly than others. Wind redistributes snowfall, piling it deeper in some regions while scouring it away in others. Terrain matters too. Valleys, plateaus, and mountain slopes influence how snow settles, and how ice flows. Over time, these variations create complex patterns within the ice, visible as layers, folds, and subtle textures. Importantly, ice sheets are sensitive to changes in climate, but they respond slowly. A few warm summers do not erase centuries of accumulation. Likewise, a brief cooling does not instantly produce ice. Ice sheets are conservative systems. They change gradually, carrying momentum from the past. This is why ice ages unfold over thousands of years rather than decades. As you imagine this process, it may help to think of ice not as something rigid and lifeless, but as something quietly active. Snow falling, layers pressing, ice flowing, landscapes adjusting beneath a slow, transparent weight. It's a reminder that some of the most powerful forces on Earth work without urgency, shaping the planet not through sudden events, but through patience and persistence. When an ice age settles into place, life does not disappear. Instead, it rearranges itself. Plants and animals respond to colder conditions by moving, adapting, and finding spaces where they can persist. Ice ages are not empty worlds of endless snow. They are patchworks of environments, each shaped by distance from the ice, by elevation, and by access to water and sunlight. As ice sheets expand, they do not cover the entire planet. Vast regions remain ice-free, especially closer to the equator and along coastlines influenced by ocean currents. These ice-free areas act as refuges, places where life can continue even during the coldest periods. Forests, grasslands, wetlands, and oceans remain active, though their boundaries shift over time. Plants are among the first to respond to changing temperatures. During colder periods, tree lines move southward or downslope. Forests that once covered large areas may thin out or retreat entirely, replaced by open tundra or steppe. Grasses, mosses, and low shrubs become more common in colder, drier climates. Pollen preserved in lake sediments and soils shows this gradual migration clearly. Species do not vanish overnight. They move slowly, following the climates they are best suited to. In many regions, plants survive ice ages by retreating into refugia, areas where conditions remain relatively mild. These refuges might exist near coastlines, in sheltered valleys, or at lower elevations. When the climate warms again, plants spread outward from these refugia, recolonizing areas that were once too cold. This repeated contraction and expansion leaves lasting marks on plant genetics, shaping patterns of diversity that can still be seen today. Animals follow similar strategies. Large mammals often migrate along the edges of ice sheets, where vegetation is available. During the last ice age, vast steppe tundra environments stretched across parts of Eurasia and North America. These open landscapes supported herds of grazing animals such as mammoths, bison, horses, and reindeer. Thick fur, fat layers, and compact bodies helped these animals conserve heat. Predators adapted as well, tracking prey across the shifting terrain. Not all animals were cold specialists. Many species associated with warmer climates survived by remaining in southern regions or moving along coastlines. Fossil evidence shows that animals like elephants, hippopotamuses, and large cats lived in parts of Europe during certain glacial periods, occupying pockets of relatively mild climate. This reinforces the idea that Ice Age environments were varied, not uniformly frozen. Ocean life also remained active throughout ice ages. Even when ice covered parts of the sea surface, the oceans beneath stayed liquid. Marine ecosystems continued to thrive, though changes in temperature and sea level altered habitats. Lower sea levels exposed continental shelves, reshaping coastal ecosystems and creating new shallow water environments. Cold, nutrient-rich waters often supported abundant marine life, including plankton, fish, and marine mammals. Ice ages also influenced freshwater systems. Glacial meltwater formed lakes and rivers at the edges of ice sheets. Some of these lakes were enormous, temporarily holding vast amounts of water before draining into the oceans. These shifting freshwater systems created new habitats and migration routes for plants and animals alike. Extinction did occur during ice ages, particularly near their ends, but it was not universal or immediate. Many species survived multiple glacial cycles. The balance between extinction and resilience depended on a species' ability to move, adapt, or find refuge. In many cases, rapid environmental change at the transition from cold to warm posed greater challenges than the cold itself. As climates warmed and ice retreated, ecosystems reorganized again. Forests returned to higher latitudes, grasslands shifted, and animals followed new food sources. The world that emerged after an ice age was not identical to the one before, but it was rich and dynamic. Life carried forward, shaped by the experience of adaptation. When you picture life during an ice age, it may help to imagine motion rather than stillness. Trees slowly spreading, animals migrating along ancient paths, oceans circulating beneath ice, and ecosystems adjusting without haste. Ice ages do not silence life. They ask it to be flexible, patient, and responsive. And time and again, life has answered. When ice spreads across the land, it changes more than the shape of the surface. It also changes how the planet handles sunlight. One of the quiet but powerful ways ice ages deepen and sustain themselves is through reflection. Snow and ice are naturally bright, and that brightness plays an important role in Earth's energy balance. Sunlight arrives at Earth constantly, but what happens to that energy depends on the surface it reaches. Dark surfaces like forests, soil, or open ocean tend to absorb sunlight. That absorbed energy becomes warmth, which can then be stored or released slowly. In contrast, light-colored surfaces reflect a large portion of incoming sunlight back into space. Fresh snow and thick ice are among the most reflective materials on Earth. When snow first begins to persist from one year to the next, this reflective quality starts to matter. A thin covering of snow can already reflect much more sunlight than bare ground. As snow deepens and spreads, the surface grows brighter. More sunlight is sent back towards space instead of warming the land. This creates a small but steady cooling effect. That initial cooling allows more snow to survive future summers. As snow remains longer, it compresses into ice. As ice spreads, the reflective area grows even larger. Each step reinforces the next. This process is known as the albedo effect. Albedo is a measure of how much light a surface reflects. High albedo means more reflection. Low albedo means more absorption. In an ice age, albedo feedback works quietly and persistently. The planet does not cool suddenly because of reflection. Instead, reflection gently tilts the balance toward colder conditions year after year. Even a small change in how much sunlight is absorbed can make a difference when sustained over thousands of years. The contrast between ice and darker surfaces is especially clear near the edges of ice sheets. At the margin, bright ice meets darker land or ocean. As ice advances, it replaces surfaces that once absorbed warmth with surfaces that reflect it. This transition helps the ice maintain itself. When ice retreats, the opposite happens. Darker ground and open water are exposed, absorbing more sunlight and encouraging warming. Open ocean plays an especially important role here. Water absorbs a great deal of solar energy. During warmer periods, when ice retreats from coastal areas, the newly exposed ocean surface can soak up heat and help moderate local climates. During colder periods, when sea ice expands, that absorption is reduced, reinforcing the cold. This difference between ice-covered and ice-free water is one of the strongest contributors to climate feedback. Albedo feedback does not act alone. It works in partnership with other slow processes. As ice reflects more sunlight and cools the planet, changes in vegetation follow. Forests may retreat, leaving behind lighter-colored grasses or bare ground, which can further increase reflectivity. At the same time, cooler temperatures can influence cloud patterns and snowfall, adding more layers of complexity. What's important to understand is that albedo feedback amplifies changes that are already underway. It does not start ice ages by itself. Instead, it takes small shifts, such as those caused by orbital changes, and gently strengthens them. Once ice gains a foothold, reflection helps it grow. Once ice begins to shrink, reduced reflection helps warmth return. This feedback loop operates slowly enough that life and landscapes can adjust around it. There is no single moment when reflection suddenly takes over. The process unfolds gradually, like a quiet adjustment of balance, rather than a dramatic tipping point. If you imagine Earth from space during an ice age, you might picture a brighter planet. White ice caps stretch farther from the poles. Snow blankets large areas of land. Sunlight glints off frozen surfaces, returning softly to space. Beneath that brightness, the planet cools just enough to sustain the ice. This reflective force is one of the reasons ice ages can persist for long periods once established. Ice helps keep itself in place, and when conditions change, reflection eases its grip just as gently. As you rest with this idea, you can let the image stay simple. Light arriving, some of it absorbed, some of it reflected, a balance shifting slowly over time. Ice does not rush this process. It simply reflects quietly, shaping the occurrence of cold and warmth across ages. As ice ages unfold, changes in the atmosphere move alongside changes on the ground. Among the most important atmospheric factors are greenhouse gases, especially carbon dioxide and methane. These gases influence how much heat Earth retains, but their role in ice ages is often misunderstood. Rather than acting as sudden triggers, greenhouse gases behave more like amplifiers, responding to temperature shifts and then reinforcing them. Evidence for this relationship comes from deep within ice sheets themselves. As snow accumulates and turns into ice, tiny bubbles of air become trapped between layers. These bubbles preserve samples of Earth's ancient atmosphere, sealed away year after year. By extracting ice cores from places like Antarctica and Greenland, scientists can measure past concentrations of gases with remarkable precision. Ice core records show a consistent pattern. During glacial periods, when ice sheets were extensive and global temperatures were lower, carbon dioxide levels in the atmosphere were also lower. Typical values during these cold phases ranged between about 180 and 200 parts per million. During warmer interglacial periods, carbon dioxide rose to around 270 to 300 parts per million. Methane followed a similar pattern, with lower concentrations during cold times and higher concentrations during warm times. One of the most interesting details revealed by ice cores is timing. Temperature changes tend to occur first, followed by changes in greenhouse gas levels after a short delay, often on the order of several centuries. This lag suggests that orbital changes and surface processes initiate warming or cooling, and greenhouse gases respond to those changes. Once they respond, they strengthen the shift that is already underway. This feedback relationship works in both directions. When the planet begins to cool, oceans can absorb more carbon dioxide from the atmosphere. Colder water holds more dissolved gas, and changes in ocean circulation can help move carbon into deeper layers. At the same time, colder and drier conditions can reduce plant growth on land, altering how carbon moves through soils and vegetation. Together, these processes gradually lower atmospheric carbon dioxide, allowing more heat to escape into space and reinforcing the cold. When the planet begins to warm, the pattern reverses. Warming oceans release some of the carbon dioxide they hold. Melting ice and thawing soils can allow gases to return to the atmosphere. As greenhouse gas concentrations rise, they help retain heat, supporting further warming and encouraging ice to retreat. This mutual reinforcement helps explain why glacial and interglacial periods can be relatively stable once established. Methane plays a quieter but similar role. Methane is released from wetlands and thawing ground, and its atmospheric concentration depends on temperature and moisture. During cold glacial periods, wetlands shrink and methane levels drop. During warmer periods, methane increases, contributing additional warming. Though methane is present in much smaller amounts than carbon dioxide, it is an effective greenhouse gas and contributes to the overall balance. What's important to keep in mind is that greenhouse gases do not act independently of the rest of the climate system. They are woven into a network of interactions involving ice, oceans, vegetation, and sunlight. No single component dominates. Instead, each responds to changes in the others, creating a self-adjusting system. In the context of ice ages, greenhouse gases help explain why small, gradual changes can lead to large shifts over long periods. Orbital variations might slightly reduce summer sunlight. Ice begins to grow. Reflection increases. Temperatures fall. Greenhouse gases decline. Each step is modest on its own, but together, they produce substantial cooling over thousands of years. From a visual perspective, you can imagine ice cores as vertical timelines. Each layer represents a year of snowfall. Within those layers, tiny bubbles mark the composition of ancient air. Reading an ice core is like reading a slow diary of Earth's atmosphere, where temperature and gas levels rise and fall together in long, gentle waves. As you settle into this section, it may be comforting to think of Earth's atmosphere not as something volatile or unpredictable, but as something responsive and patient. Greenhouse gases adjust gradually, moving in step with the planet's broader rhythms. They follow temperature rather than racing ahead of it. They reinforce what is already happening, helping ice ages deepen and warm periods endure. In this way, greenhouse gases are part of the planet's long conversation with itself. A conversation carried out slowly, through ice and air, across tens of thousands of years. Beneath the slow growth of ice and the quiet shifts in the atmosphere, the oceans continue their long, steady work. Covering most of Earth's surface, the oceans act as the planet's largest reservoir of heat. They absorb, store, and transport energy, smoothing out temperature differences over vast distances. During ice ages, this buffering role becomes especially important. Water has a high capacity to store heat. Compared to land or air, the ocean can absorb large amounts of energy with only a small change in temperature. This means that even as the climate cools, the oceans change more slowly than the air above them. In this way, the seas act as a stabilizing force, preventing abrupt swings and helping the climate system move gradually. Ocean currents are the main way this stored heat is redistributed. Warm surface waters flow from the tropics toward higher latitudes, while colder, denser water sinks and moves back toward the equator at depth. Together, these movements form a global circulation system that connects all of Earth's oceans. During ice ages, this circulation does not stop, but it can shift in subtle ways. One of the most influential changes involves the balance between saltwater and freshwater. As ice sheets grow, they lock large amounts of fresh water onto land. This makes the remaining ocean water slightly saltier and denser, which can affect how and where water sinks. Conversely, when ice sheets begin to melt, pulses of fresh water flow into the oceans. This fresh water is lighter than salt water and can spread across the surface, forming a thin layer that resists mixing. In some regions, especially the North Atlantic, these freshwater pulses can temporarily slow deep water formation. This does not require a global change in temperature. Instead, it alters regional climate by changing how heat is transported. When warm surface currents weaken or shift, areas that once received steady warmth can cool, even while the global average temperature remains relatively stable. Evidence for these shifts comes from marine sediments and ice cores. Layers of sediment on the ocean floor preserve changes in temperature, salinity, and biological activity. They show that during glacial periods, ocean circulation patterns differed from those of today. Some currents weakened, others strengthened, and new pathways emerged as sea levels fell and coastlines changed. The exposure of continental shelves during ice ages also influenced ocean behavior. When sea levels dropped by as much as 120 meters, shallow seas disappeared and coastlines moved outward. This reshaped marine ecosystems and altered how currents flowed along continental margins. Narrower ocean passages and new land barriers redirected water, subtly changing the movement of heat. Sea ice plays another role in this system. As sea ice forms, it insulates the ocean beneath, reducing heat loss to the atmosphere. At the same time, The formation of ice releases salt into the surrounding water, making it denser and encouraging it to sink. This process helps drive circulation in polar regions. When sea ice melts, it introduces fresh water at the surface, again influencing density and flow. These interactions mean that the oceans can both respond to and influence ice ages. They help distribute the effects of cooling and warming, sometimes delaying or moderating changes. In certain cases, they can also create regional variations, where some areas experience significant cooling or warming independent of the global average. It's important to remember that oceanic changes during ice ages unfold over long timescales. Currents do not abruptly switch direction. Fresh water does not instantly transform circulation. Each adjustment takes years, decades, or centuries to fully express itself. The result is a climate system that evolves smoothly, with momentum and memory. If you imagine the oceans during an ice age, you might picture them as vast, dark expanses, quietly moving beneath a cooler sky. Currents continue their slow paths. Heat is carried, stored, and released with patience. Even as ice advances on land, the oceans remain active, connecting distant regions and helping the planet maintain balance. In this way, the oceans serve as Earth's quiet stabilizers. They do not dominate the Ice Age story, but they ensure that it unfolds slowly, with few sudden turns. Their steady presence allows ice ages to breathe in and out, shaped by motion that is slow, deep, and enduring. To understand why Earth enters long periods of cooling, it helps to look far beneath the surface, into processes that unfold over millions of years. Long before ice sheets expand or oceans adjust their circulation, the slow movement of Earth's crust sets the background conditions that make ice ages possible. Plate tectonics, mountain building, and the reshaping of continents all play a quiet but essential role. One of the most important tectonic shifts in Earth's climate history occurred when Antarctica drifted into its current position over the South Pole. This movement was not sudden. Over tens of millions of years, the southern continents gradually separated. As Antarctica became isolated, a new ocean current was able to form around it. This current, known as the Antarctic Circumpolar Current, flows endlessly around the continent, connecting the Atlantic, Pacific, and Indian Oceans. The formation of this current had a profound effect. By circling Antarctica without interruption, it cut off the flow of warm tropical waters that had previously reached the continent. Isolated from warmth, Antarctica cooled enough for ice to persist year-round. Over time, a massive ice sheet formed and grew. Once established, this ice sheet further cooled the region through reflection, reinforcing its own stability. This event marked the beginning of a long-term cooling trend that helped set the stage for the ice age we live in today. Continental positions matter because land behaves differently from water. Land can accumulate snow and ice. Ocean cannot. When large landmasses sit near the poles, the planet becomes more capable of sustaining long-lasting ice. Plate tectonics determines where continents are located, how oceans connect, and how currents move. Each of these factors influences how heat is distributed across the globe. Mountain building adds another layer to this story. When continents collide, they push rock upward, forming vast mountain ranges. The Himalayas, Andes, Rockies, and Alps all rose during different phases of Earth's tectonic history. As mountains rise, they expose fresh rock to the atmosphere. Rainwater interacts with this rock through chemical weathering, slowly drawing carbon dioxide out of the air. This process, known as silicate weathering, acts over millions of years. As carbon dioxide is removed from the atmosphere, the planet gradually cools. The carbon is eventually transported to the oceans and locked into sediments, where it can remain for long periods. This slow drawdown of greenhouse gases helps lower global temperatures and can contribute to long-term cooling trends. The uplift of large mountain ranges also influences wind patterns and precipitation. Mountains can redirect atmospheric circulation, creating rain shadows and altering where moisture falls. Over time, these changes affect vegetation, erosion, and the movement of carbon through ecosystems. All of these processes subtly interact with climate, reinforcing cooling when conditions allow. Another tectonic event that influenced Earth's climate was the formation of the Isthmus of Panama around 3 million years ago. When North and South America became connected, ocean currents between the Atlantic and Pacific were disrupted. This change strengthened the Atlantic circulation, increasing moisture transport to high northern latitudes. In colder conditions, that moisture fell as snow, contributing to ice sheet growth in the northern hemisphere. These geological changes did not directly cause ice ages on their own. Instead, they created a climate system that was more sensitive to other influences, such as orbital cycles. Tectonics set the baseline. Orbital changes provide the timing. Together, they guide the planet into and out of ice ages. What makes tectonic influences especially calming to consider is their pace. Continents move at rates comparable to the growth of fingernails. Mountains rise and erode slowly, balancing uplift with weathering. Ocean gateways open and close over spans far longer than human history. There is no rush in these processes. They are steady, deliberate, and patient. If you imagine Earth across this timescale, you might picture continents drifting like slow ships across a deep ocean. Mountains lifting gradually, then wearing down. Currents forming, strengthening, and stabilizing. These deep changes prepare the planet for colder or warmer eras, long before ice appears. In this way, tectonics acts as Earth's long-term climate architect. It doesn't dictate the details of individual ice advances or retreats, but it shapes the broad conditions under which ice ages become possible. Beneath every glacier lies a foundation built by the slow movement of rock, guiding the planet through cycles that span millions of years. As ice sheets grow across continents, one of the most visible changes they bring is a quiet reshaping of the planet's shorelines. Ice ages do not just alter temperatures on land. They change where the oceans reach, how coastlines are drawn, and how land and sea connect. These changes unfold slowly, but their effects are widespread. When glaciers and ice sheets expand, they store enormous amounts of water that would otherwise be part of the oceans. During the height of the last major glacial period, roughly 20,000 years ago, global sea level was about 120 meters lower than it is today. This drop did not happen suddenly. It accumulated gradually as ice sheets thickened and spread, locking fresh water onto land. As sea levels fell, coastlines moved outward. Shallow continental shelves that are now submerged or exposed as dry land. These areas often formed broad plains, gently sloping toward the ocean. Rivers extended farther across the landscape, carving valleys that are now hidden beneath the sea. In many regions, what we think of as the coast today lay far inland from its Ice Age position. These exposed shelves created new connections between land masses. One of the most well-known examples is the land bridge that once linked Siberia and Alaska. This broad expanse of dry land allowed plants, animals, and eventually humans to move between Asia and North America. Similar connections existed elsewhere. Britain was joined to mainland Europe. Parts of Southeast Asia formed a single landmass. Islands became peninsulas, and peninsulas became continuous stretches of land. The lowering of sea level also affected marine ecosystems. Coral reefs, which require shallow, sunlit waters, shifted their positions as coastlines moved. Some reefs grew upward to keep pace with falling seas, while others were left stranded. Estuaries and coastal wetlands were reshaped or relocated. New habitats formed, while others disappeared, all in step with the changing shoreline. As ice ages ended and ice sheets began to melt, the process reversed. Water returned to the oceans and sea levels rose. This rise unfolded over thousands of years, gradually flooding the exposed shelves. Valleys became bays. Plains turned into shallow seas. Rivers shortened as their mouths moved inland. The modern coastlines we know today are the result of this slow inundation. Evidence of these changes is preserved beneath the oceans. Submerged river channels, ancient shorelines, and layers of sediment all record the steady advance of the sea. In some places, coral reefs stacked on top of one another reveal repeated cycles of falling and rising sea level. Each layer marks a pause in the long transition from cold to warm. Sea level change during ice ages was not uniform everywhere. The weight of ice sheets pressed down on the land beneath them, causing it to sink slightly. At the same time, regions beyond the ice experienced a subtle uplift as the planet's crust adjusted to the shifting load. When ice melted, the process slowly reversed. Land that had been compressed began to rebound upward, while other areas adjusted downward. This ongoing movement, known as glacial isostatic adjustment, continues even today in some regions. These adjustments mean that local sea level histories can differ from the global average. Some coastlines experienced greater changes, others less. But the overall pattern remains consistent. Ice ages draw water out of the oceans. Warm periods return it. From a broader perspective, sea level change is one of the ways ice ages reshape Earth without drama. There is no single moment when the ocean suddenly rises or falls. Instead, shorelines drift. Landscapes transform gradually. Life adapts to the changing boundaries between land and sea. As you imagine this process, you might picture coastlines breathing in and out with the rhythm of the ice. Land expanding outward during cold periods, then slowly surrendering space back to the sea during warmth. The planet adjusts its edges quietly, guided by the slow movement of ice and water. In this way, ice ages leave their signature not only in frozen regions, but along every shore. They redraw the map of the world over long stretches of time, reminding us that even the boundary between land and ocean is part of Earth's patient, ongoing motion. As ice sheets and glaciers move across the land, they leave behind a record written directly into the surface of the Earth. This record does not announce itself loudly. It appears in broad valleys, smooth rock faces, scattered stones, and quiet plains of fine sediment. Long after the ice has melted, these features remain, telling the story of motion that unfolded slowly and steadily. One of the most recognizable landforms shaped by ice is the U-shaped valley. Before glaciers arrive, rivers carve narrow V-shaped valleys as they cut downward through rock. When ice fills these valleys, it presses against both the floor and the sides. As the glacier flows, it grinds away at the rock evenly, widening and deepening the valley. When the ice eventually retreats, the valley is left with a broad, rounded floor and gently sloping walls. These U-shaped valleys can be found in many mountainous regions today, quiet reminders of ancient ice. In coastal areas where glaciers once reached the sea, this carving created fjords. Fjords are long, narrow inlets with steep sides, often extending far inland. They form when glacial valleys are flooded by rising seas after the ice melts. The depth and shape of fjords reflect the thickness and power of the ice that once occupied them. Their calm waters and towering walls give them a still, almost timeless quality. As glaciers move, they carry enormous amounts of debris. Rocks become frozen into the ice, traveling along with it. When the ice slows or melts, this material is deposited, often in distinctive patterns. Moraines are ridges or mounds of unsorted rock and sediment left behind at the edges or ends of glaciers. Terminal moraines mark the furthest advance of ice, while lateral moraines trace the sides. These features act like quiet boundary markers, showing how far the ice once reached. Drumlins are another signature of moving ice. These smooth, elongated hills are shaped beneath flowing glaciers. They tend to align with the direction of ice movement, forming clusters that resemble gentle waves frozen into the landscape. Though their exact formation is still studied, drumlins offer clear evidence of ice flowing steadily over the ground. Sometimes glaciers leave behind individual stones that seem out of place. These are called erratics. An erratic might be a large boulder resting on bedrock of a completely different type. Its presence reveals that it was carried from far away, transported by ice rather than by rivers or gravity. Erratics are among the simplest and most striking clues of past glaciation, appearing almost like punctuation marks in the landscape. Not all glacial shaping involves carving. Ice also influences the land through deposition. As glaciers grind rock into fine particles, winds can carry this material beyond the ice margins. Over time, layers of wind-blown silt, known as loess, accumulate across wide areas. These loess plains can be very fertile, supporting rich soils long after the ice age ends. In this way, glaciers contribute not only to erosion, but also to the creation of environments that sustain life. The movement of ice also smooths and polishes bedrock. Rocks caught at the base of a glacier scrape against the ground, leaving behind striations, fine grooves that indicate the direction of flow. In some places, bedrock appears almost sculpted, with rounded forms and subtle textures that reflect the pressure and persistence of ice. What makes these landscapes especially calming to consider is the timescale of their creation. No single storm, earthquake, or flood produces them. They are shaped by motion, measured in centimeters per day, sustained over centuries and millennia. The power of ice lies not in speed, but in patience. As you imagine these forms, you can picture a glacier moving slowly, barely perceptible from one moment to the next. Beneath it, the land adjusts, reshaped grain by grain. When the ice finally retreats, the landscape remains, carrying the memory of that long contact. Today, many of the world's most serene and striking landscapes owe their shape to ice ages. Wide valleys, clear lakes, rolling hills, and fertile plains all bear the influence of ancient ice. These features invite stillness and reflection, echoing the calm processes that formed them. In this way, ice ages leave a quiet legacy. Long after the cold has eased, the land continues to speak, softly, of glaciers that once passed over it. To understand ice ages, scientists rely on records that form quietly and persist for long periods of time. These records do not come from a single source. Instead, they emerge from many parts of the natural world, each preserving a piece of the climate's history. When combined, they allow us to reconstruct past ice ages with surprising clarity, even though they unfolded tens or hundreds of thousands of years ago. One of the most direct sources of information comes from ice itself. In places where ice sheets have remained stable for long periods, such as Antarctica and Greenland, snowfall accumulates year after year without melting. Each winter adds a new layer, gently pressing down on the layers below. Over time, these layers compress into solid ice, preserving a chronological record much like the rings inside a tree. By drilling deep into ice sheets, scientists can extract long cylinders of ice called ice cores. These cores contain layers that stretch back hundreds of thousands of years. Each layer holds subtle clues about the climate at the time it formed. The thickness of the layer can reflect how much snow fell in a given year. The texture and chemistry of the ice reveal information about temperature and atmospheric conditions. One of the most valuable features of ice cores is the presence of tiny air bubbles trapped inside. As snow compresses into ice, small pockets of air become sealed off. These bubbles preserve samples of ancient atmosphere, allowing scientists to measure past levels of gases such as carbon dioxide and methane. In this way, ice cores act as frozen time capsules, holding direct evidence of how Earth's atmosphere has changed across glacial and interglacial periods. Ice cores also preserve other materials. Dust carried by wind settles onto snow and becomes trapped in ice, offering clues about dryness and wind patterns. Volcanic ash layers mark distant eruptions, providing time markers that can be matched across different records. Even changes in snowfall chemistry can reveal shifts in ocean circulation or vegetation patterns far away. Beyond the ice sheets, the oceans provide another long-term archive. On the seafloor, layers of sediment accumulate slowly over time. Tiny particles settle out of the water, forming thin layers that build up over thousands of years. These sediments contain microscopic shells from marine organisms, along with minerals and organic material that reflect ocean temperature and ice volume. One of the key tools used to read ocean sediments involves isotope ratios. Some elements exist in slightly different forms, known as isotopes. Oxygen isotopes, for example, behave differently depending on temperature and the amount of ice on land. During cold periods, more of the lighter oxygen isotope becomes locked into ice sheets, leaving the oceans slightly enriched in the heavier form. By measuring these ratios in fossil shells, scientists can infer changes in global ice volume and ocean temperature over time. While isotope measurements can sound technical, their meaning is simple. They allow researchers to see when ice was expanding and when it was melting. Over long sediment cores, these measurements form smooth curves that rise and fall in rhythm with ice ages, providing an independent confirmation of patterns seen in ice cores. On land, lakes and wetlands offer another kind of evidence. Pollen grains released by plants settle into sediments and are preserved for long periods. Each plant species produces pollen with a distinctive shape, allowing scientists to identify which plants were present at different times. By studying layers of pollen, researchers can track how vegetation shifted during ice ages, showing forests retreating, tundra expanding, and plants migrating with changing climates. Fossils add further detail. Remains of animals and plants preserved in sediments reveal where species lived and how ecosystems changed. Cave formations, such as stalagmites, grow slowly from dripping water and record changes in rainfall and temperature through subtle chemical variations. Even soils can preserve traces of ancient climates through their structure and composition. What makes these records especially powerful is how well they agree with one another. Ice cores, ocean sediments, pollen records, and fossils all tell consistent stories. When ice cores show cooling, pollen records show tundra spreading. When sediments indicate rising sea levels, coastal fossils reflect shifting shorelines. This agreement gives confidence that the patterns we see are real and robust. Importantly, these records form without intention. Snow falls, sediment settles, plants release pollen. Over time, these natural processes create archives that quietly document Earth's climate history. No single record tells the whole story, but together they create a detailed picture of ice ages unfolding gradually. As you imagine these forms, you can picture a glacier moving slowly, barely perceptible from one moment to the next. Beneath it, the land adjusts, reshaped grain by grain. When the ice finally retreats, the landscape remains, carrying the memory of that long contact. Today, many of the world's most serene and striking landscapes owe their shape to ice ages. Wide valleys, clear lakes, rolling hills, and fertile plains all bear the influence of ancient ice. These features invite stillness and reflection, echoing the calm processes that formed them. In this way, ice ages leave a quiet legacy. Long after the cold has eased, the land continues to speak, softly, of glaciers that once passed over it, shaping the world with steady, unhurried care. During ice ages, plant life does not vanish. Instead, it adjusts its position on the planet, responding steadily to cooler temperatures and shifting seasons. The story of plants during ice ages is one of movement, endurance, and quiet continuity. Forests retreat, grasslands expand, and tundra spreads, all following the slow cycles of climate rather than reacting to sudden change. As ice sheets grow and temperatures fall, the zones where different plants can survive begin to shift. In higher latitudes and at higher elevations, conditions become too cold for trees to grow. In these regions, forests thin and eventually give way to tundra. Tundra landscapes are dominated by hardy grasses, mosses, lichens, and low shrubs that can tolerate short growing seasons and cold soils. These plants grow close to the ground, conserving heat and resisting wind. Evidence from pollen records shows that tundra environments once extended far south of their current ranges during glacial periods. In parts of North America and Europe, regions that are now forested were once open, treeless landscapes. This expansion did not happen abruptly. As climates cooled, trees produced fewer seeds at their northern limits, while tundra plants gradually moved in. Over centuries, the balance shifted. Forests did not disappear entirely. Many tree species survived ice ages by retreating into refugia, areas where conditions remained suitable despite the overall cooling. These refugia were often located in southern regions, along coastlines, or in sheltered valleys. For example, during the last ice age, deciduous trees such as oaks and beeches persisted in parts of southern Europe, while coniferous forests extended farther south in North America. These refugia acted as reservoirs of biodiversity. When climates warmed and ice retreated, trees spread outward from these protected areas, recolonizing newly available land. This process left lasting marks on plant genetics. Modern forests often contain genetic signatures that trace back to their Ice Age refuges, revealing patterns of isolation and reconnection across thousands of years. Southward movement was a common response to cooling. As temperatures fell, many tree species shifted their ranges toward lower latitudes, where sunlight and warmth remained sufficient. In mountainous regions, plants moved downslope to escape colder conditions at higher elevations. These migrations were slow, unfolding over many generations, guided by seed dispersal and changing soil conditions. Grasslands also played an important role during ice ages. In many regions, vast steppe-like environments developed, especially in areas with low precipitation. These open landscapes supported cold-adapted grasses and herbs, which thrived in the cooler, drier climate. Such environments were especially common in regions bordering ice sheets, where conditions were too cold for forests, but not cold enough for permanent ice. Plants also adapted physiologically to Ice Age conditions. Many developed strategies to survive freezing temperatures, such as producing antifreeze-like compounds in their tissues or timing their growth to brief summer windows. Perennial plants stored energy underground, allowing them to regrow quickly when conditions improved. These adaptations helped plants endure repeated cycles of cold and warmth. Pollen preserved in lake sediments provides a detailed timeline of these changes. Layer by layer, pollen records show which plant species dominated at different times. During glacial periods, pollen from grasses and tundra plants becomes more abundant. During interglacial periods, tree pollen increases as forests return. This alternating pattern mirrors the rhythm of ice ages themselves. What's striking is how orderly these transitions appear in the record. There is no sudden collapse of vegetation. Instead, plant communities reorganize gradually. Some species become more common, others less so. Over time, entire ecosystems shift their position, moving across the landscape in response to climate. As ice ages end and warmth returns, plants reverse their migrations. Trees expand northward and upslope. Tundra retreats. Soil development accelerates as organic matter accumulates. the landscape becomes more diverse again, supporting a wider range of plant life. As you imagine this process, you might picture tree lines slowly sliding across the land, pollen drifting down into lakes, and seeds spreading into new territory. Plants respond to ice ages not with urgency, but with patience. Their story is written in layers of sediment and in the genetic memory of modern forests, a testament to life's ability to adapt over long stretches of time. During ice ages, animal life does not diminish into simplicity. Instead, ecosystems often become rich mosaics of movement, adaptation, and diversity. The colder world supports a wide range of species, each finding its place along the shifting margins of ice, tundra, grassland, forest, and sea. The animals of the ice ages were not living in a single frozen environment, but across many interconnected habitats. One of the defining features of Ice Age ecosystems was the expansion of open landscapes. In many regions, vast steppe tundra environments developed, stretching across large parts of Eurasia and North America. These open plains supported herds of grazing animals adapted to cold and dryness. Among the most well-known were woolly mammoths, woolly rhinoceroses, bison, horses, and reindeer. Thick fur, layers of fat, and compact body shapes help these animals conserve heat and endure long winters. These large herbivores shaped the landscape as they moved. Grazing maintained open areas, prevented tree encroachment, and supported a rich mix of grasses and herbs. In turn, these herds supported predators that were equally adapted to the cold. Cave lions, wolves, and large bears followed the movements of prey, tracking seasonal changes in vegetation and snow cover. Cold-adapted species were not limited to mammals. Birds, insects, and smaller animals also adjusted their ranges and behaviors. Many species developed seasonal migration patterns, moving to milder areas during the coldest months and returning when conditions improved. Others remained year-round, relying on specialized behaviors such as burrowing, hibernation, or changes in diet. What's especially interesting about Ice Age fauna is the presence of warm climate species alongside cold-adapted ones. Fossil evidence shows that animals such as elephants, hippopotamuses, and large cats lived in parts of Europe during glacial periods. These animals occupied pockets of relatively mild climate, often in southern regions or along coastlines. This coexistence highlights the patchwork nature of Ice Age environments, where different climates existed side by side. Marine ecosystems were also shaped by ice ages. Lower sea levels exposed continental shelves, creating extensive shallow water habitats. Cold, nutrient-rich waters supported abundant plankton, which in turn sustained fish, seabirds, and marine mammals. Seals, whales, and walruses adapted to the presence of sea ice, using it as a platform for resting and breeding. Over the course of an ice age, animal communities changed gradually. Species ranges shifted, populations rose and fell, and new ecological relationships formed. This turnover was usually slow, allowing ecosystems to reorganize without sudden collapse. Many species survived multiple glacial cycles, adjusting their distributions with each shift in climate. Toward the end of the last ice age, some large animals disappeared. The reasons for these extinctions are complex and varied, involving changes in climate, habitat, and human presence. What's important in this context is that extinction was not a defining feature of ice ages themselves. For most of their duration, ice ages supported thriving, diverse animal life. Animal fossils provide a window into this world. Bones preserved in sediments, caves, and permafrost reveal where species lived and how they moved. Trackways frozen into ancient mud show animals walking across landscapes that no longer exist. Together, these records show a dynamic, populated world, shaped by cold, but not emptied by it. As you imagine animals during ice ages, you might picture herds moving slowly across open plains, predators following at a distance, birds migrating along familiar routes, and marine life circulating beneath ice-covered waters. Movement, not stillness, defines this world. Ice ages challenge animals, but they also create opportunities. New habitats emerge, old ones shift, and species adapt in response. Through patience and flexibility, animal life finds ways to persist, leaving behind a legacy that continues to shape ecosystems today. As ice ages reshaped the planet, humans became a part of that changing world. Long before modern societies formed, early human species lived through cycles of cold and warmth, adapting their routines, tools, and habits to the demands of a cooler climate. Their story during ice ages is not one of constant struggle, but of steady adjustment and quiet ingenuity. Several human species experienced ice age conditions. Neanderthals lived across Europe and Western Asia during repeated glacial and interglacial periods. Their bodies were well suited to cold environments. Shorter limbs and broader torsos reduced heat loss, while large nasal passages helped warm and humidify cold air before it reached the lungs. These physical traits reflect long-term adaptation rather than sudden change. Early Homo sapiens also encountered cold climates as they expanded beyond Africa. As our species moved into Eurasia, they entered regions shaped by ice age conditions. Archaeological evidence shows that humans learned to manage cold through behavior rather than biology alone. Clothing made from animal hides provided insulation. Sewing tools, such as bone needles, suggest garments were carefully fitted and layered for warmth. Fire played a central role in Ice Age human life. Hearths provided heat, light, and a place to cook food. They also created social centers, places where people gathered, rested, and shared time together. The presence of controlled fire allowed humans to occupy regions that would otherwise have been too cold to sustain them. Shelter was another important adaptation. Humans used caves, rock overhangs, and built structures from wood, bone, and hides. In some regions, mammoth bones formed the framework of dwellings, covered with skins to block wind and cold. These shelters were often temporary, reflecting a seasonal way of life that followed animals and changing resources. Seasonal movement was a defining feature of human life during ice ages. Rather than settling permanently in one location, groups moved across familiar landscapes, returning to the same areas at different times of year. This mobility allowed them to take advantage of seasonal abundance while avoiding the harshest conditions. Roots were learned, remembered, and passed down through generations. Diet also reflected adaptation to cold environments. Ice Age humans relied heavily on animals for food, clothing, and tools. Large herbivores provided meat, fat, bones, and hides. Plants remained part of the diet when available. especially in milder seasons and regions. This flexible approach to food helped humans remain resilient across changing conditions. The archaeological record shows that humans did not merely survive ice ages, but developed cultural traditions during them. Artifacts such as carved objects, pigments, and early art suggest symbolic expression and shared meaning. These cultural practices likely played a role in strengthening social bonds, which are essential for cooperation and survival in challenging environments. What stands out about humans in a cold world is their capacity for planning and learning. Knowledge about where to find shelter, when animals migrated, and how to prepare for winter was accumulated slowly and shared within groups. This knowledge allowed humans to anticipate change rather than react to it. Ice ages did not halt human development. Instead, they formed a backdrop against which key aspects of human behavior took shape. Cooperation, tool-making, communication, and adaptability were all reinforced by life in variable climates. Cold conditions encouraged innovation, but always within a rhythm that allowed time to adjust. As you imagine humans during ice ages, you might picture small groups moving across open landscapes, tending fires at dusk, repairing clothing, and watching the seasons shift. Their lives were closely tied to the land and its cycles. Ice ages were not obstacles to be overcome once, but ongoing conditions to live within. In this way, humans became part of the Ice Age ecosystems they inhabited. Like plants and animals, they adapted gradually, responding to cold with patience, knowledge, and community. As ice ages lowered sea levels and reshaped coastlines, the geography of the world opened and closed pathways that no longer exist today. These changes did not happen quickly, but over thousands of years, they created temporary bridges of land that connected continents, islands, and regions. Through these quiet openings, plants, animals, and humans moved, slowly expanding into new territories. One of the most important features of Ice Age geography was the exposure of continental shelves. When large volumes of water were locked into ice sheets, global sea level dropped by as much as 120 meters. Shallow seas retreated, revealing wide expanses of dry land along the edges of continents. These newly exposed areas were often flat and gently sloping, making them easy to traverse over long distances. The most well-known of these land bridges is Beringia, the region that once connected northeastern Asia and northwestern North America. During glacial periods, the Bering Strait was not a narrow stretch of water, but a broad landmass hundreds of kilometers wide. This land bridge supported grasses, shrubs, and animals, forming a cold but productive environment rather than a barren corridor. Animals moved across Beringia long before humans did. Herds of grazing mammals followed vegetation as climates shifted, gradually expanding their ranges. Predators followed prey. Over time, entire ecosystems crossed between continents. Much later, humans made the same journey, moving into the Americas in stages as conditions allowed. Importantly, these migrations did not happen all at once. Movement occurred slowly, often over many generations. Groups advanced, paused, and sometimes retreated as climates fluctuated. The land bridge itself appeared and disappeared multiple times across different glacial cycles, opening and closing the route repeatedly. Elsewhere in the world, similar connections formed. Britain was once joined to mainland Europe by a wide plain, often referred to as Doggerland. This landscape supported rivers, wetlands, forests, and abundant wildlife. Humans lived there for thousands of years before rising seas gradually flooded the area, turning it into the seabed of the North Sea. In Southeast Asia, lower sea levels connected islands into larger landmasses. These connections allowed animals and early humans to spread across regions that are now separated by water. When sea levels rose again, populations became isolated on islands, leading to distinct evolutionary paths. This isolation shaped biodiversity and cultural development alike. Migration pathways were not limited to land bridges. Lower sea levels also changed coastlines, creating extended coastal plains that people and animals could follow. Coastal routes may have provided reliable food sources and relatively stable climates, making them attractive pathways for movement during ice ages. As ice retreated and seas rose, these pathways closed. Land bridges flooded, coastlines moved inland, and populations that had once been connected became separated. This separation encouraged regional adaptation. Over time, isolated groups developed distinct languages, cultures, and genetic traits shaped by their specific environments. What's striking about Ice Age migration is how strongly it reflects patience and timing. No one crossed continents in a single journey. Expansion happened slowly, guided by environmental opportunity rather than urgency. Routes were learned, remembered, and reused when conditions permitted. From a broader perspective, ice ages acted as gatekeepers of movement. Cold periods opened paths by lowering seas. Warm periods closed them again. This rhythm influenced where species lived, how they spread, and how isolated populations became. As you imagine these migrations, you might picture coastlines stretching outward, land rising where water once flowed, and long paths forming quietly across the planet. People and animals move along them without hurry, following familiar patterns of survival and curiosity. In this way, ice ages shaped not only climates and landscapes, but the very map of life on Earth. Through slow changes in sea level and geography, they guided movement across continents, leaving a lasting imprint on the distribution of species and cultures we see today. When ice ages come to an end, they do not do so abruptly. There is no single moment when the cold releases its hold. Instead, the transition unfolds slowly, guided by the same gentle forces that brought the ice into place. Warming arrives gradually, giving the planet time to respond, adjust, and reorganize. One of the first shifts happens far from the surface, in the slow rhythms of Earth's orbit. Over thousands of years, changes in the tilt of Earth's axis and the shape of its orbit alter how sunlight reaches the planet. In particular, summers in high-latitude regions begin to receive slightly more energy. These changes are subtle, but they matter deeply. Ice sheets are sensitive to summer warmth. When summers become just warm enough that snow melts more completely, the balance begins to change. At first, this does not look dramatic. Ice still covers vast areas. Winters remain cold, but each summer removes a little more ice than the previous one. Snow that once lingered now disappears. Meltwater forms along the edges of ice sheets, carving small channels and pooling in shallow basins. The ice thins slowly, losing mass not through sudden collapse, but through steady retreat. As ice thins, its reflective surface begins to shrink. Darker land and open water appear at the margins, absorbing more sunlight than ice ever could. This additional absorption gently encourages further warming. It is not a runaway process. It is a quiet easing, a gradual shift in balance that favors melting over accumulation. At the same time, the atmosphere responds. As temperatures rise, oceans begin to release some of the carbon dioxide they hold. Thawing soils and expanding vegetation also influence how carbon moves through the system. Ice core records show that carbon dioxide levels tend to rise during these warming phases, following the initial temperature increase. This rise helps reinforce the warming, making it easier for ice to continue retreating. The retreat of ice sheets reshapes the landscape. Rivers swell with meltwater, carrying sediment into valleys and seas. Large glacial lakes form at the edges of the ice, sometimes draining slowly, sometimes finding new outlets as the land adjusts. Vegetation begins to reclaim ground that was once too cold to support it. Mosses and grasses arrive first, followed by shrubs and eventually trees. Animal life responds as well. Species that had followed the ice margins move northward or upslope, tracking the habitats they depend on. Forest-dwelling animals expand their ranges as woodlands return. Marine ecosystems adjust to rising sea levels and changing coastlines. These shifts happen over many generations, allowing ecosystems to reorganize without sudden disruption. Importantly, the end of an ice age does not mean the end of ice altogether. Even during warm interglacial periods, large ice sheets can persist in polar regions. The difference lies in their extent and stability. During warm phases, ice retreats to higher latitudes and elevations, becoming a quieter presence rather than a dominant force shaping the continents. The pace of this transition is one of its most calming features. From the peak of a glacial period to the full establishment of an interglacial climate can take thousands of years. This extended timeline allows soils to develop, rivers to find new courses, and species to adapt gradually. There is no need for urgency in the system. Earth moves at its own speed. As ice ages end, the planet does not return to a fixed state. Warm periods are part of the same long cycle. They too are temporary in geological terms. Ice may advance again in the distant future, when orbital conditions shift once more. For now, though, the easing of an ice age represents a phase of expansion and recovery. If you imagine this transition visually, you might picture ice margins slowly pulling back, leaving behind wet ground that dries and greens over time. Meltwater streams weave quietly across the land. New plants take root in soil freshly released from beneath the ice. The cold does not vanish. It simply loosens its grip. In this way, the end of an ice age is less like an ending and more like a change in tempo. The planet moves from contraction to expansion, from ice-dominated landscapes to more varied ones. Everything happens with patience, allowing Earth systems to settle gently into their next phase. Prior to the ice ages we usually imagine, Earth experienced periods of cold that were far more extensive in scale. These events are known as snowball Earth episodes, and they stand apart from later ice ages in both severity and scope. They remind us that Earth's climate history includes extremes far beyond anything seen in recent geological time. Snowball Earth refers to a series of glaciations that occurred during the Cryogenian period, roughly 720 to 635 million years ago. During these times, evidence suggests that ice extended across much of the planet, possibly reaching equatorial regions. Unlike the ice ages of the past few million years, where ice sheets were largely confined to higher latitudes, Snowball Earth involved near-global ice coverage. Geological clues supporting this idea are found in rocks formed at low latitudes that show clear signs of glaciation. These include glacial deposits, scratched rock surfaces, and distinctive sediment layers known as dropstones. Dropstones form when rocks embedded in ice fall into softer sediments below, leaving visible disruptions. Finding such features in regions that were once near the equator suggests that ice was present even in tropical zones. Despite the dramatic name, Snowball Earth does not necessarily imply that every part of the planet was sealed beneath thick ice at all times. Some models suggest that areas of thinner ice or open water may have existed, especially near volcanic regions or along fractures in the ice. These openings would have played an important role in maintaining Earth's systems during these extreme cold phases. One of the most remarkable aspects of Snowball Earth is that life persisted. Evidence indicates that microorganisms survived beneath the ice, in the oceans, and possibly in pockets of meltwater. Subglacial oceans remained liquid due to geothermal heat from Earth's interior. Hydrothermal vents continued to supply warmth and nutrients, supporting ecosystems even while the surface was frozen. Photosynthetic life may also have found refuge. In areas where ice was thin or translucent, light could penetrate enough to support basic photosynthesis. Additionally, cracks and open leads in the ice may have allowed sunlight to reach the water below. These refuges, though limited, would have been sufficient to carry life through long periods of cold. Snowball Earth episodes eventually came to an end, and their resolution reveals an important difference between these events and later ice ages. During Snowball Earth, volcanic activity continued to release carbon dioxide into the atmosphere. Normally, carbon dioxide is balanced by weathering processes that remove it from the air. But when the planet is covered in ice, weathering slows dramatically. Over millions of years, carbon dioxide accumulated, gradually strengthening the greenhouse effect. Eventually, this buildup reached a point where warming began to overcome the global ice cover. Once melting started, the retreat of ice accelerated, leading to a relatively rapid transition to warmer conditions. Geological evidence suggests that the end of Snowball Earth may have been marked by intense weathering and the deposition of unusual carbonate rocks as the climate stabilized. Importantly, Snowball Earth has not repeated since the Cryogenian. Several factors likely prevent its return. The arrangement of continents has changed, reducing the likelihood of ice spreading so extensively. The sun has become slightly brighter over time, providing more baseline energy. Biological activity has increased, influencing how carbon moves through the atmosphere and oceans. Together, these factors make a return to near-global glaciation much less likely. When compared to the ice ages of recent geological history, Snowball Earth stands as an extreme outlier. Later ice ages involved large ice sheets and significant cooling, but they always left wide regions of the planet free of permanent ice. Life, ecosystems, and geological processes continued across these ice-free zones, maintaining continuity. As you reflect on Snowball Earth, you might imagine a planet wrapped in ice, quiet and reflective, yet still alive beneath the surface. Heat rises slowly from below. Water circulates beneath frozen layers. Life persists patiently, waiting for conditions to change. Snowball Earth reminds us that Earth's climate system is capable of profound change, but also of recovery. Even in its coldest chapters, the planet maintained pathways for life and stability, setting the stage for the rich and varied world that followed. Over the longest stretches of Earth's history, climate does not drift endlessly toward heat or cold. Instead, it moves within broad limits, guided by slow processes that act like a planetary thermostat. This balance does not operate on human timescales, and it does not prevent short-term extremes. But over millions of years, it helps keep Earth within a range where oceans remain liquid and life can persist. At the center of this long-term stability is the carbon-silicate cycle. This cycle moves carbon slowly between the atmosphere, the oceans, the land, and Earth's interior. It works quietly, without urgency, shaping climate through gradual exchange rather than sudden shifts. Volcanoes are one part of this system. Deep within the planet, carbon is stored in rocks and magma. When volcanoes erupt, they release carbon dioxide into the atmosphere. This process happens continuously, even during times when volcanic activity seems minimal. Over very long periods, these emissions add carbon dioxide to the air, gently encouraging warming. Opposing this input is chemical weathering. When carbon dioxide dissolves in rainwater, it forms a weak acid. As this rain falls onto exposed rock, it slowly breaks minerals down. During this process, carbon is removed from the atmosphere and transported by rivers to the oceans. There, it becomes part of carbonate minerals, eventually settling onto the seafloor. Over time, these carbonate sediments are carried into Earth's interior through plate tectonics. Subduction zones pull oceanic crust downward, returning carbon to the mantle. From there, it may remain stored for millions of years before being released again through volcanism. This completes the long loop. What makes this cycle act like a thermostat is how it responds to temperature. When Earth becomes warmer, weathering tends to increase. Warmer temperatures often bring more rainfall, and faster chemical reactions break down rock more efficiently. This enhanced weathering removes carbon dioxide from the atmosphere, gently cooling the planet over time. When Earth becomes cooler, weathering slows. Ice may cover large areas of land, and chemical reactions proceed more slowly. With less carbon dioxide being removed, volcanic emissions gradually build up in the atmosphere. Over long spans of time, this accumulation promotes warming, easing the planet out of colder states. This feedback does not operate quickly. It unfolds over hundreds of thousands to millions of years. It does not prevent ice ages from forming, nor does it stop warm periods from occurring. Instead, it defines the outer boundaries of Earth's climate, preventing permanent runaway freezing or irreversible overheating under natural conditions. The carbon-silicate cycle helps explain why Earth has experienced ice ages, warm periods, and even extreme events like Snowball Earth, yet has always returned to a state where oceans persist and life continues. It provides a background stability, a slow correction that works regardless of short-term variability. Mountains play an important role in this system. When continents collide and mountains rise, fresh rock is exposed at the surface. This newly uplifted rock weathers more easily, increasing the removal of carbon dioxide from the atmosphere. Over time, this can contribute to long-term cooling trends. The uplift of major mountain ranges has coincided with shifts toward cooler global climates in Earth's past. Rain, too, is part of the picture. Each drop that falls onto bare rock participates in this slow exchange. There is nothing dramatic about it. No single storm alters the climate. But over millions of years, the cumulative effect of rainfall, rock, rivers, and sediment quietly shapes the composition of the atmosphere. Seen this way, Earth's climate system is not fragile in the long-term sense. It is resilient but slow. It allows wide swings, but it resists permanent imbalance. Ice advances and retreats. Seas rise and fall. Forests expand and contract. Through it all, carbon moves steadily through its cycle. As you rest with this idea, you might imagine carbon drifting gently through time, released from deep within the earth, carried through the air, dissolved in rain, locked into stone, and eventually returned to the depths. The movement is continuous, unhurried, and largely unseen. Earth's thermostat does not aim for comfort or precision. It does not respond to years or centuries. It works on scales so large they are difficult to fully grasp. Yet it has kept the planet within a life-supporting range for billions of years. In this quiet balance between volcanism and weathering, between release and removal, Earth maintains its long-term stability. The process is slow enough to fade into the background, steady enough to be trusted, and vast enough to hold the planet gently in place as time continues forward. In the broad language of geology, the present moment sits within an ice age. This can sound surprising at first, because much of the world today feels warm, familiar, and stable. But ice ages are defined not by constant cold everywhere, but by the presence of large, persistent ice sheets at the poles. By that definition, the Earth has been in an ice age for millions of years, and it remains in one now. The current phase is known as the Holocene interglacial. An interglacial is a warmer interval within a longer ice age, a period when ice retreats from much of the continents, but does not disappear entirely. The Holocene began roughly 11,000 years ago, following the retreat of the last major continental ice sheets in the northern hemisphere. Since then, global temperatures have remained relatively mild and stable, compared to the deep cold of full glacial periods. This stability is one of the defining features of the Holocene. Seasonal cycles continue. Glaciers persist in polar regions and high mountains, and snow comes and goes each year. But the large ice sheets that once covered much of North America and Europe are gone. Sea levels have stabilized near their current positions. Ecosystems have had time to settle, expand, and diversify. From a geological perspective, this period is brief. 11,000 years is a short pause in a pattern that stretches back millions of years. Yet for human history, it has been expansive. Nearly all of agriculture, written language, cities, and recorded culture developed within this narrow window of relative climatic calm. It is important to understand that this calm does not imply stillness. The climate continues to vary, responding to subtle changes in Earth's orbit, ocean circulation, volcanic activity, and biological processes. However, these variations remain within a relatively narrow range compared to the swings between glacial and interglacial extremes. This allows long-lived ecosystems and human societies to remain rooted in place. Polar ice remains a key marker of the ice age we are in. Antarctica holds vast ice sheets that have persisted for tens of millions of years. Greenland retains a large ice cap that waxes and wanes over glacial cycles. Mountain glaciers exist on every continent except Australia, quietly responding to local conditions. These bodies of ice are reminders that the planet has not exited its ice age state, only shifted into a warmer phase within it. One of the most useful ideas here is the difference between geological time and lived time. On a human scale, thousands of years feel unimaginably long. On a planetary scale, they pass like moments. The Holocene feels stable because it is stable relative to the slow heartbeat of ice ages. It is not static, but its changes are subtle enough to fade into the background of daily experience. Orbital cycles that influence ice ages continue today. The same slow variations in tilt, wobble, and orbital shape that once favored the growth of ice sheets are still unfolding. In the absence of other influences, these cycles would eventually favor cooler summers in the far north again, allowing ice to begin accumulating. From a purely natural perspective, the next glacial phase would be expected tens of thousands of years into the future. For now, the Earth remains in an interglacial balance. Forests grow where ice once stood. Rivers follow paths carved by meltwater. Soils continue to develop on landscapes released from ice long ago. Seasonal snow comes and goes, echoing the deeper rhythm of glaciation in a gentler form. Thinking about the present as part of an ice age can bring a sense of perspective. It places modern experience within a much longer story, one that continues regardless of observation. The ice at the poles does not rush. The seasons do not hurry. The planet maintains its slow, steady patterns. As you reflect on this, you might imagine polar ice lingering quietly through centuries, while snow falls and melts elsewhere with each passing year. The larger structure remains in place, even as surface details change. This is the nature of Earth's present state. The ice age we are in is not defined by urgency or extremes, but by continuity. It is a long chapter with many variations, of which the Holocene is a calm page. And like all pages in Earth's history, it exists as part of a larger, ongoing story that moves forward at its own unhurried pace. When viewed from a long enough distance, the future of ice ages appears less like a sequence of events and more like a continuation of rhythm. The same forces that shaped past glacial cycles are still present, still moving, and still interacting quietly in the background. Earth's orbit continues its slow variations. Ice responds gradually. Oceans circulate, rocks weather. Nothing about this system suggests an endpoint, only ongoing motion. Under natural conditions, the timing of future glacial periods is largely governed by orbital mechanics. Subtle changes in Earth's tilt, wobble, and orbital shape alter how sunlight is distributed across the planet, especially in the high northern latitudes. When summers become cool enough that winter snow no longer melts completely, ice can begin to accumulate. Over thousands of years, this accumulation may grow into continental ice sheets once again. Based on these orbital patterns alone, scientists estimate that the next major glacial period would normally be expected many thousands of years from now. The exact timing varies depending on which orbital factors are emphasized, but the general picture remains consistent. Glaciation is a slow response to slow forcing. Nothing begins abruptly, and nothing unfolds on a human timescale. What makes the long view forward especially calm is the recognition of limits. Even with detailed models and extensive records, there are boundaries to what can be known. Earth's climate system contains countless interacting parts, some of which behave in non-linear ways over long durations. Volcanic activity varies. Tectonic plates continue to move. Biological systems evolve and reshape landscapes. These influences introduce uncertainty, but not chaos. The uncertainty exists within a framework of stability. Importantly, uncertainty here does not mean unpredictability in the short term. It means that exact dates and precise magnitudes fade as timelines extend into tens of thousands of years. The overall direction remains clear. Ice ages come and go. Warm periods return. The planet adjusts continuously without needing intervention or acceleration. From this perspective, the future is not something rushing toward us. It is unfolding at the same pace it always has. Ice sheets respond slowly to changes in summer sunlight. Oceans absorb and release heat gradually. Carbon moves through rocks, water, air, and living systems at speeds measured in millennia. These processes do not react to moments. They respond to patterns. One helpful way to imagine this is to picture Earth's orbit continuing silently through space. Each year passes almost indistinguishably from the last. Over thousands of years, the orientation shifts slightly. Over tens of thousands, those small shifts accumulate into meaningful changes in seasonal balance. Ice notices, land notices, oceans notice, but the response remains measured and gradual. Even when glaciation eventually resumes, it does so unevenly. Ice begins in specific regions. It grows and retreats locally before spreading more broadly. Landscapes transform slowly. Ecosystems adapt. Life reorganizes rather than disappears. This has been the pattern repeatedly across Earth's history. The long view forward also highlights continuity across past, present, and future. The same processes that shaped ancient ice ages are shaping the present interglacial and will shape future ones. There is no dividing line where one era ends and another begins suddenly. Transitions overlap. Phases blend into one another. The Earth system carries memory forward through ice layers, sediments, and landscapes. On a human level, this perspective can feel grounding. It reminds us that the planet operates on timescales far beyond individual lifetimes, cultures, or civilizations. Change is real, but it is not hurried. Stability emerges from motion rather than stillness. As you consider the future from this long view, you might imagine ice responding slowly to distant orbital shifts, thousands of years from now. You might imagine glaciers beginning as quiet accumulations of snow, unnoticed at first. Or you might simply imagine Earth continuing as it always has, adjusting gently, without urgency. The future of ice ages does not demand attention. It does not call for prediction or alarm. It exists as part of a continuous process, unfolding whether observed or not. And in that continuity, there is a sense of calm. Earth's systems persist. Patterns repeat. Time stretches comfortably beyond immediate concern. This is the long view forward. Not a destination, but an ongoing rhythm, moving at a pace that invites patience rather than anticipation. As this journey through ice ages comes to a close, there is no sharp ending to reach. Ice ages themselves do not conclude cleanly. They fade into the background, continuing quietly as part of Earth's deeper motion. What remains is a sense of scale and a sense of calm. Across millions of years, ice has formed and retreated without pause for observation. Snow has fallen in places no one watched. Glaciers have flowed in silence. Oceans have risen and lowered their edges with patience. These processes did not seek attention, and they did not require urgency. They simply unfolded. Ice ages remind us that much of Earth's activity happens beyond immediate awareness. Change does not always announce itself. Often, it accumulates gently, layer by layer, until it reshapes landscapes in ways that feel timeless once complete. Valleys deepen, shorelines move, forests migrate. Ice leaves quiet signatures and then withdraws. Seen this way, ice ages are not interruptions in Earth's story. They are part of its steady breathing. Cold expands. Warmth returns. Balance shifts and settles again. Nothing is rushed, and nothing is wasted. Even long periods of cold support life, adaptation, and continuity. As attention softens, it can help to imagine the planet continuing on its own. Snow falling at the poles. Ice forming slowly under its own weight. Time stretching wide enough that individual moments dissolve into patterns. The Earth does not hurry through these cycles. It moves at the pace required for stability. You do not need to hold every detail. The facts can fade now, leaving behind only the rhythm they describe. Ice ages exist, whether remembered or forgotten. They pass through deep time without demand, shaping the world quietly. In this way, ice ages become part of the background, like distant weather on another continent or tides moving far offshore. Present, ongoing, and steady. Earth continues, with or without observation. As rest approaches, you might let your focus drift toward that slowness, toward snow settling gently, toward ice forming unseen, toward systems at rest, balanced within motion. The story continues on its own, and you are free to rest within it.